Also the environmental impact. There are areas where we need to strictly minimize it. It depends on the accessibility of the place, if it is readily accessible with trucks, with machineries or not. So there are several issues that we have to take into account. Basically, we concentrate on the hydraulic design. We don't concentrate on the structural design. We don't speak about how to design the concrete structure. We focus, as I said, on the hydraulic design. First of all, let's take into account that barrages are divided in three categories. The last one, temporary barrages, we don't consider it because usually they don't need to be designed. They are frequently used by farmers, for instance. What they do is at the end of the winter, during the low flow season, they go over the river and with stones, they typically build small dams by putting stones one above the other and therefore diverting part of the flow into canals that are made every year in order to simply divert water to the fields where they need water for irrigation. They are frequently used. Usually they are not designed. Keep in mind that in order to do this, at least in Italy, we should always apply and ask a permission, because water in Italy and in most of the countries is a public good and therefore cannot be used without asking permission. And this is a problem because it frequently happens that people, sometimes in good faith, they take water without applying for it and without asking permission. Like many people also in this region bring their own well in the courtyard, which is very easy, because today to dig a well is extremely easy. You don't need to excavate anymore. You just need to with a number, to put a pipe into the soil. It's very easy. And many people, as I said, in good faith, don't know that for using water, anybody has to ask a permission, whatever the amount of water that is used. And this is because water is a public good. And this is extremely important, especially in view of the need to ensure that in rivers we have an environmental flow that is preserved. We will speak about it. These are temporary barrages. We don't focus on them because, as I said, usually they don't require design. And then there are the two categories of permanent barrages, which are regulated barrages and unregulated ones. What's the difference? The difference is that regulated barrages are equipped with machineries like gates or regulated sluiceways. Sluiceways are, in essence, ways where the water passes through the barrage. They can be different types. They can be bottom discharges, they can be weirs. Basically, they are passages, and these sluiceways can be regulated because you may equip the sluiceway with a gate. A gate in Italian is called paratoia, is a way to block the passage of water. And what is the meaning of a regulated barrage? The meaning is that if you want to keep the water level upstream at a constant position, no change during winter, during summer, you have to regulate the flow by opening or closing gates. When you get a lot of water from upstream, you open the gates because you don't want the water level to raise up over a certain limit. When you get reduced flow or no flow, you need to close the gates. because if you want to keep the water level with no inflow, you need to close the gates, or almost closed. And this is the purpose of a regulated barrage. Of course, the regulated barrage requires maintenance and management, because somebody, either through a computer code or directly, needs to open and close the gates. Now they are managed in an automatic way, but still there is some human intervention that is required, at least to check that everything is going fine. So it's a bit complicated. The management is complicated. We require human resources, and we require resources in general. Unregulated barrages, there is no regulation, so less requirements for resources, simpler management, but we have to take into account that the water level upstream may change. When there is a lot of flow, we have the water level raising. When there is low flow, the water level is decreasing, of course, like in a natural river, So some people say that unregulated barrages are less impacting because there is almost no change on the dynamic of the river. There is a change because you take some water, but still there is variability in the river. Variability, keep in mind, that is important for the preservation of the ecosystem. The ecosystem is trained against variability, and if you suppress variability, the ecosystem suffers. On the other hand, some people say that unregulated barrages are more dangerous because there is no control, and therefore, if you get a lot of flow from upstream, you have the water level raising upstream and downstream. While a dam, which is regulated, of course, because you have to store water during winter and release water during summer, has the advantage that downstream a dam, you have a regulation, and the regulation also allows to prevent floods, for instance. So the dam is not only a risk, it may offer some reduction of the risk in particular situation. When a huge flood is coming upstream, if the dam has the capacity to store water, of course it is reduced the river flow downstream, which means a decrease of the risk. So it's basically a compensation, and the rule of thumb is that when you work on a huge river and your structure is important because it aims to get a lot of water, then regulation is needed. When you work on mountain rivers, small infrastructures, we tend to make them unregulated because they are cheaper and the maintenance is simpler. We focus on unregulated ones because these are the structures that are most frequently designed. Today there is an increase of interest for small hydropower plants and for using surface water for irrigation because of the development of agriculture, and again the water food energy nexus, which requires getting more energy, more renewable energy in a sustainability context. And hydropower is a renewable energy, it's a clean energy. There is some impact, but it's considered a clean energy. And therefore, these small hydropower plants are often composed by a turbine, etc., but also a river barrage that allows to withdraw water. And therefore there are a lot of opportunities for designing these small structures. Regulated barrages, big structures over big rivers, were built a lot in the past. We realized that the environmental impact is very severe, and therefore today they are less frequently designed. Keep in mind that all the big rivers of Europe are regulated, with one exception, which is the Po River. Along the Po River there is only one big barrage, which is the hydropower plant of Isola Serafini. It's the only one. And there were plans for barraging the Po River, even recently, but there were concerns related to the environmental impact because we observed during over other rivers like the Danube, like the Rhino River in Germany, they were equipped with a lot of barrages, also to favor navigation, but people realized that the impact is extremely relevant because there is reduced variability, there is reduction of the river flow at the end of the story because you want to store water in order to ensure navigation, and therefore the river flow is reduced, and therefore the concentration of pollutants increases. So there are several concerns. Okay, let's have a look anyway at this figure, which is it's a link on Google. I don't remember the name. I have an amnesia. Google Earth. It is a link over Google Earth. You can zoom it, and this is a barrage over the Danube, and there is the name here of the barrage. What is interesting here to do is to zoom it. Because if you zoom it, you can get to a level of detail that is extremely refined. And you can see that there is a road that passes over the barrage. And you see the gates here. I hope that you can see the mouse. These are the gates. And these ways are equipped with the gates because it's regulated. Here on the two sides, because here the Danube draws the border here between, I don't remember, let me see. I think it's between Hungary and, okay, we will check it. It's not really important. And there are two hydropower plants, one per each side, in order to make sure that the two neighboring states can also use this barrage for producing hydropower. The barrage creates a jump, a difference in elevation between upstream and downstream. So if instead of allowing the water to freely flow, you force the water to flow through a turbine, you produce hydropower. Keep in mind that barrages may have multiple purposes. They can be conceived for instance, irrigation, but when you release the water downstream, you can turbine it, therefore getting some hydropower. And this is something that we look for. In a sustainability context, we look for multiple uses. And this is an example. What's interesting to see here is the presence of the navigation lock, which is here. I'm not sure whether you know what is a navigation lock. It's a passage for the ships, because given that another purpose of this barrage is to make sure that the Danube can be traveled with the ships. Of course, when there are these jumps, we need to build a structure in order to allow the ships to climb up or to jump down. And these are the navigation locks. I'll give you a detail just in a second of what a navigation lock is. And look at the downstream end. There is this gate. Let's increase, okay. This gate here, which I'm highlighting with the mouse, it's a Porta Vinciana. It's called, also in English, Porta Vinciana, which is a lock, a gate, which, by the way, it seems that was not invented by Leonardo da Vinci, but the purpose of this gate is that the pressure of water from upstream closes the gate, helps to keep the gate closed, which means that when you are accumulating the water upstream, basically the pressure of water helps the gate to keep to prevent the leakage. Okay, let's see a detail on navigation lock. I hope that there is the link here. Let me see. 1 second. There is not the link here because this is a former version of the web page. There is already online the new version. Let me see. Because I'm using two different versions of my web page. One in order to be projected, and another one to be read. And if we go to the online version, it's already updated. Because I updated this yesterday, and It is automatically updated every day in both versions, but it's still not updated. Let's see. But even here I can see the link, so I need to check. I need to check, but let me. Navigation log. Okay, this is the page that I wanted to show you. I need to check why there is no. Okay, this is how it works. So basically, the navigation lock is done. Okay, let me see. I think I need to enlarge it. No way. So this is an example, a sketch of a boat that is climbing from downstream. So basically there is the Porta Vinciana that is first open up there, number one, and the boat gets into the middle stage, and then the boat gets into here. The Porta Vinciana is closed, and therefore there is it's opened the upper Porta Vinciana in order to let water flow from upstream to downstream, therefore raising the boat. If we go down, you see there is a partial opening of this Porta Vinciana in order to flow the water to flow here, and then the upper Porta Vinciana is completely open, and the boat can go upstream, and a similar procedure is repeated for jumping down. Okay, and I did this to you. So let's focus on the design. The first thing that we need to design for river barrage is the water withdrawal. So to estimate the design flow. With design flow, we mean the flow of the diverted water. And this is to be designed based on the flow duration curve. So here there is something that is repeated on what we already know. Basically, we need to estimate the flow duration curve, and we also need to estimate the water demands. And there are two possibilities, two possible options. Either we have plenty of water in the river, and therefore, if there is plenty of water, we estimate the design flow based on demands, meaning that we don't get all the water from the river, we get only a part, and therefore water resources availability is not a problem. If it's not a problem, we need to estimate the demands, and also the demands for the future. So we have to base on demographic expansion, estimation of demographic expansion, estimation of agricultural expansion, so there is a social analysis that is to be done, and then basing on the expected lifetime of the structure, we estimate the water demands for the future, and we design basing on them. Still, sometimes it may be convenient to get more water because we can turbine the excess water, for instance, and release it back into the river. There is also the opposite situation, where your demands are, in any case, higher of water resources availability. In this case, what you do is to base the estimation of design flow on the flow duration curve. You get all the water from the river in order to compensate, at least in part, the demand. You can't get all the water because you have to release into the river the environmental flow, which is a minimum flow to be released into the river in order to preserve the ecosystem and the fluvial habitat. Keep in mind that this is a relatively new requirement. In the past, we designed dams, we designed barrages in order to get all the water from the river. And this was up to 1980, 1990 in Europe. Then rules were introduced in member states imposing to release the environmental flow, also for existing structures. And this is a compelling requirement, compelling and also very demanding requirement. In some cases, it introduced some crisis, because, of course, once that a community is used to have a certain flow at disposal, if you reduce the flow after the community got used to it, it's a problem. And also keep in mind that monitoring the environmental flow, it's extremely difficult. It's difficult to make sure that it is released, because sometimes it is complicated to measure it. So even if the manager of the structure is in a good faith, sometimes it's not easy for them to make sure that they are releasing the environmental flow. And also it's very difficult to monitor. Many of these structures are placed in locations that are not easy to access, and therefore monitoring is a bit complicated. So still today, it's an issue. It's an issue because you know, it's something that is evolving. But this is the most frequent situation. Very frequently, water demands are higher than water resources availability. Okay, so we know how to estimate the flow duration curve. We, in particular, talked about the estimation of the flow duration curve basing on data and basing on rainfall runoff modeling. I just wanted to mention to you a third opportunity or more opportunities for the ungauged locations, which is the most frequent case. Data are available for gauged locations. Where we don't have data, we can use rainfall runoff models, or we can use other undirect method of estimation. And there is one method that I wanted to introduce to you at this stage, because it's a kind of B-plan that we can use in those situations where data are not available and building a rainfall runoff model may be complicated or not feasible for whatever reason. This is a simple option that is frequently used in practice, which is to refer to a close-by gauged location. So for instance, let's suppose that we have to build a dam here. This is our site of interest. And this is ungauged. So what we do is to refer to a gauged close-by location. Gauged close-by location. Close-by means the closest one. And then here we have a flow duration curve, Q, D. Here we have our flow duration curve, and here we have a contributing area which we called AG. Contributing area means area of the catchment that is contributing to the river flow in the location, in the gauged location. In the site of interest, which is ungauged, the flow duration curve is unknown, of course, Q, D, this is question mark. And we have a contributing area which is AUG, A ungauged. So all what we know is to know the contributing area, and then what we do is that the unknown flow duration curve is obtained by rescaling through the ratio AUG divided by AG, rescaling the observed flow duration curve UD, gauged. does rescaling mean? It means that Q ungauged of whatever duration d is expressed by simply multiplying the corresponding Q gauged for the same duration d by the ratio A UG divided by AG. So if you have the same contributing area, you simply equate the two flow duration curves. If the contributing area at the ungauged location is, for instance, half of the contributing area at the gauged location, you simply multiply the observed flow duration curve by 1/2 and you get the unknown flow duration curve. It's a simple rescaling based on the ratio of the contributing areas. You understand that it's extremely simple. It's also uncertain. By intuition, you understand that being very simple, it's also uncertain. But you also understand that if the two locations are not very far away, it has a kind of, it is reasonable. I mean, if the two locations are close by, it's reasonable. You have the same climate, same geology, same river dynamics, and therefore it is reasonable to assume that the river flow is proportional to the catchment area. Usually the river flow doesn't depend only on the catchment area. It also depends on the climate, it depends on the geology, it depends on the evapotranspiration. But if the two locations are located close by, you can assume that they have the same climate, the same geology, the same orography, same evapotranspiration, and therefore you can just rescale the flows by the contributing areas. Of course, it doesn't work if the two locations are located very far away. Different climate, different orography, different geology, completely different situation. We know that very different rivers have very different specific river flow. Specific means per unit area. If it rains a lot, we have a high specific river flow. If the catchment is very small, we said that the specific river flow is very high. If the catchment is larger, we said that the specific river flow is lower. But if the two catchments are close by and not very different in size, that's fine. So you have also to be concerned when this ratio is very different from 1. If the ratio is 0.01, which means that there is a 100 difference in the size, 2 orders of magnitude, then you have to be careful. If a catchment is 1 square kilometer and the other one is 100 square kilometers, the behavior is different. But if one catchment is 20 square kilometers and the other one is 40, that's fine. This is called hydrologic similarity. So when you say, I simply applied hydrologic similarity, it means that you are scaling a river flow by the contributing area of the catchment. There is also a branch, a class of procedures for doing the same thing, which is called the regionalization techniques. We don't focus on them. I just want you to know this term. If you say that you use a regionalization, there is also hydrologic similarities included in regionalization, means to estimate the river flow based on regional behaviors, so behavior of the region. And there is a class of method which includes several techniques that can be used to the purpose. Again, we don't focus on them. Now, let's suppose that we know the flow duration curve, and how can we design the design flow? Okay, let's first of all consider that when we design water withdrawal river barrages, usually we are required to make at least two designs, a preliminary one and a final one. In some cases, we are required to make three of them. The preliminary design helps, the purpose is to get the permission to move forward. So basically the authorities, I told you just some minutes ago that we need to apply and to apply for a permission to use, a governmental permission to use the water. And the authorities requires that we present a preliminary design. They don't want us to make a final design and then they say no. So they ask for a preliminary design, which is simple. Still you have to define, of course, the design flow. And then once the permission is obtained, you move forward with the final design. For the preliminary design, we often use rules of thumb in order to get the estimated design flow. And a typical rule of thumb, which I already mentioned to you, I'm quite sure, is that for a water withdrawal, the design flow is, by looking at the duration curve, the flow that corresponds to a duration between 30 and 60 days. This is usually the optimal design flow for a water withdrawal. So once that you know the flow duration curve, you go in between the flows with the duration of 30 and 60 days. You go somewhere in between depending on your needs, and you fix the design flow in this way. And then, for the final design, you need to make a cost-benefit analysis. We already discussed that if you take a design flow that is higher, you have increased benefit because you increase the volume of water that you withdraw, but there are more expenses, more costs. If you decrease the design flow, conversely, you reduce the benefit, but you also reduce the costs. There is an optimal value that is to be identified through a cost-benefit analysis. You estimate the benefit, you estimate the cost, construction costs and maintenance costs, and then you find the design flow that gives the best compromise. Okay, once that you define the design flow, we can estimate the water volume that is withdrawn on average with uncertainty. Remind the flow duration curve how it's defined in a year. And we can also compute these two indexes which we already mentioned. The water withdrawal index, which is the ratio between the design flow QP and the average flow into the river. And the water use index, which is the ratio between the average flow diverted from the river and the average flow in the river. I think I already introduced these when we spoke about the flow duration curve. These are very simple indexes. I may ask them at the exam, just because it's a simple question. Okay, now, with the design flow we are done. We are done because we discussed already extensively about the flow duration curve. And now you can see why the flow duration curve is important with more detail. Now let's talk about the structure of a typical barrage. And there is a figure here. Let me increase its size, or let me do like this. Okay, perfect. So this is a handmade sketch, handmade by me. So you can recognize that it's not perfect, but you know, the engineers usually are not good artists. And today we are saved because we use AutoCAD and electronic programs, computer programs to draw. In the past, it was the main problem of the engineer was, you know, hand drawing. Okay, let's move forward. So, this is the river flowing from upstream to downstream. What are the main structures? Usually, we build lateral walls to drive the flow in correspondence on the barrage. These walls are not always present. Usually they are built in order to prevent erosion of the hill slopes in correspondence of the barrage. And then we have the transversal structure. The transversal structure, the purpose of this transversal structure, which is not regulated, again, is to fix the elevation of the riverbed and to stabilize the elevation of water upstream. This transversal structure during high flows needs to be surmounted and with good efficiency, because when there are floods, we don't want the river level upstream increasing a lot. And therefore we need to set up a main spillway, which is located here, which is overpassed only by the water in excess of what? In excess of the environmental flow and the diverted flow. The first flow that we have to release is the environmental flow. When there is water in excess with respect to the environmental flow, we then start to divert water up to the diverted flow, which is the design flow. When there is water in excess beyond environmental flow plus diverted flow, then the water in excess must be